Hello YouTube, RJ. Been busy on the bench. Wanted to show you what I've been working on. Working on the beginnings of the VFO. I've got a little circuit here, very simple little circuit here, which I'll jump over the computer and show you in a minute, show you what we're up to. But what this is all about is building a biasing circuit for these variactors that will tune linear through the range. And so since variactors themselves don't react linear to voltage change, remember variactors we've talked about before are diodes that have much more capacitance than most diodes. All diodes have some capacitance, but these have much more, and the purpose of them is to allow you to have a electrically changing capacitor. You can have a variable capacitor by applying a reverse bias voltage, and varying the voltage changes the capacitance, and you can use this to tune radios. And so that's what I'm working on. I'm trying to get a design that will tune linear for our VFO. And so let me jump over to the computer and show you the circuit and show you what we're working on. Okay, here's the little simple circuit. Showing a linear regulator in here, 7809, 9-volt positive regulator. In reality, on the breadboard, I've got my linear power supply feeding 9 volts in, but the end result would be this is the circuit that we'd be operating with. It brings voltage into, and because of the way LT Spice works, I've created a pot that I could adjust in a step statement and a parameter statement by taking two resistors. This would be the upper half of the pot and the lower part of that pot, and this is your wiper. And so I can adjust these two, and using this parameter, as I step through 10% of each value, so I get 10 turns of this pot, I reduce this one by the amount this one creates, and therefore I create an equal ratio of these resistors to simulate a pot for us. So what I'm going to do now is I'm going to show you that with a linear pot, what we're going to get out over to our variactors here is a linear voltage output. So let's simulate this. Let's pick up our voltage here, and notice all of the voltages, each step, every 1000 K that you turn the pot, you get the exact same amount of voltage increase. That makes total sense. It's a linear pot. If you've got a linear pot and you need it to not be linear, you need to make it work in other than a linear fashion, there's a way to do that. And the way you do that is you take a resistor from the wiper of your pot and you connect it to ground. You parallel a resistor with the lower part of your pot between the wiper and the ground. Let's do a 1K, and let's take a look at how this works now. Notice that my voltages at the low end are bunched up. Each equal turn of the pot gives me a smaller voltage change, getting bigger and bigger and bigger. Well, that's kind of what we want for the variac, because the variac moves very quickly when you first start applying voltage. As the voltage is coming up, it drops its capacitance very quickly. But in a nonlinear method, more of an exponential method, it gets slower and slower in the reduction of capacitance. It takes a lot more voltage. So if we can make a pot that gives us more and more voltage the farther we go, we can counteract the effects of that in the variactor and try to make a more linear tuning circuit. Now, it's never going to be perfect, but how good can we get it? I don't know. Let me go show you what I'm doing, how I'm testing this to see what different resistor values here will gain us in our circuit. So what I'm doing is I've got my little circuit hooked up here, and I'm feeding in 9 volts into it, and I'm using the pot to create a variable voltage. My meter over here is telling me the voltage, so it's 1.918 at the moment. And I look up here and I can see my capacitance on my LCR, and I'm using the average. It's 146. So what I do is I have this mark set to a certain point here, and what I do is I take a measurement and rotate exactly one turn. That gives me 10 data points. So I'm ready to move to the next data point. So here's what I'm going to do. I'm going to rotate this around and line it right back up in the same spot. I'm lining up on the pins that the wire solder to. And I look over here and I turn the average off and hit the average again to reset the average and let it start averaging on what the average capacitance reading is there. And I take my voltmeter, 2.589, and I look up here and I say she's averaging 117 picofarad. Okay. And literally I just go through that 10 times on the pot. And what I've done is I've already done this numerous times. And I started out with just the pot, the linear pot, got a reading through it. And then I've started putting resistors between the wiper and ground to change the linearity of the pot. Take my readings, graph them out, and I'm looking for what sways the linearity of this pot enough to try to offset the nonlinearity of these variactors to get me a nice smooth linear tuning across the band of our oscillator. So I only have one more reading on this run. I'll rotate around and line it up precisely again, which is right at the stop. And I take the reading again, 8.765 for voltage, reset my average, give it a minute to get some averages. I'm coming up with about 36 picofarad. Now that that's done, we've got to move over to the computer and I'll enter that information in and chart it out. Okay, so here we are on a copy of one of the spreadsheets that we're working with. And we're going to fill this one out. So we're going to start at the volts, and I'm going to put in all of the voltages, just because it's quicker to do that than go back and forth between the voltage and the capacitance. So I just go down the list and put them all in. I'll jump to the end of this. So here you can see, this is my voltage. You can see that it's not linear, okay? This is the capacitance. You can see it's coming down. It's got a little S to it, but it follows this fitted line, which this line is generated to show me if it was perfectly linear, what it would look like. And we don't do too bad here, actually. We do quite well. Let me show you what it's like without a resistor, just the linear pot itself. Well, you can see our capacitance fit is very poor. It doesn't follow at all. You can see the kind of difference we can make. Now, the other thing I noticed is we only got a spread from the most capacitance to the least capacitance of 236, but with the extra resistor in, we got a little lower voltage, and that brought our top end a little higher, and that got us 261 picofarad. So this is the amount of tuning capacitor I'll have with this configuration. This isn't really that bad. It's not perfect, but I'm going to continue on. Let me do a bunch of other resistors. We'll come back and we'll take a look at all of them and see how they came out and see if I can get anything better than this. So, okay, so I've been working away with getting my data and putting it in spreadsheets and figuring out the same way over and over again with different resistors. And I've come to a conclusion. Let me jump over and show you what I come up with. I think you're going to be surprised. I was. Okay, I'm done, and I want to walk you through the findings that I found. And this spreadsheet here is, as I showed you before, this is just the pot, no changes, no resistor across the wiper to ground. And as you can see, I get a very linear voltage going up, and I get a very unlinear capacitance. Look at the big steps in capacitance each turn of the pot. And then I get down here, and at the very end, it flattens out and hardly changes. And you can see that. Here's the spread. We get 236 picofarad change overall, but 89 of that happens in the bottom end. Bottom end meaning the highest capacitance. So from here to halfway down. And the reason I call that the bottom is your higher capacitance is going to make lower frequency. So this is the bottom of your VFO tuning. And then the last half of your rotations will give you 5 picofarad. Very nonlinear, not good at all. You can see the fit line here. It's horrible. Now we're going to go and throw a 680 ohm. Now, why did I start at 680? Well, I set and figured that when you put these resistors in, you're going to be putting current through this resistor. Depending on where you have the pot set, it could be the full 9 volts. And so if you get below 680 ohms, you're starting to get where you're burning a lot of current, generating a lot of heat you don't want in your VFO. And so going too low is a problem. I felt just barely comfortable at 680. I wouldn't want to go lower than that. So I started at 680, and we can see some interesting things happen with our voltage. It definitely put a curve in the voltage. And you can see that we've helped this dramatically. It's not perfect by no means, but dramatically better. The form fit line shows you just how much more linear we are. Dramatic difference with just that 680 ohm resistor. And we go here and we get a spread of 304, and we've opened this up quite a bit. Now our bottom has 86, and we've actually swung it the other way. The top now has 159 picofarad change and only 86 at the bottom. So far from perfect, but better. So then we go to a 1K and try that. And this is looking a little better, believe it or not. You've got a better fit line, 261 spread. The bottom is 98 picofarad to the middle, and the top frequencies are 81 picofarad. So that's not too bad. That's looking pretty good. I think that would be reasonable. But then you go to the 1.5, and bear in mind, as you go up, another benefit is we're less and less wasted current and heat. You know, we're getting in a range now, it's not a big deal, but go up to 1.5 and hello, this isn't looking bad at all. That's a really nice fit. Spread of 323, which is good. But look at this. The bottom frequency, the bottom half turn of the VFO gives you 160 picofarad change. The next half of your rotation into the higher frequency gives you 163. That's when the error of my measurement. We're only talking 3 picofarad variation from one end of the dial to the other end of the dial. That's dead on in my book. I think that's fantastic. We can look at 2.2. Now we went so far as we're causing some interesting things to happen. I didn't like this kink near the middle here. Linearity here is spot on, but you can see that our tops and bottoms are getting more varied. So I think we've went too far at this point. This to me was too far. So it looks like I'm going to be using a 1.5 parallel resistor from the wiper to ground to kind of linearize out the VFO. So that's kind of what I've been working on. So let me get back to the bench. Okay, and with that, we're done. Thanks for tuning in. Hope you learned a little something. Hope you enjoyed your time with me today. And I hope to see you in the next video.